Hey everyone, Mr. Fransky here. This is going to be just a rundown of the problems from the blue Taylor series worksheet. So you got this sheet before we knew how to do error, but I'm actually going to go through all of the parts of these problems so that this will be useful to you if you're reviewing for the test or whatever it is. So you might not understand some parts of these problems, but I'm going to just do them all and take the parts that you know how to do, and the sheet actually tells you which ones you can't do yet if you haven't done 9.3. Or 9 through 9.5 really is what you need to do the alternating series parts of this. So let's jump in. So we're going to start with this one. We have this piecewise function, which isn't really that piecewise, right? It's this function, this cosine minus 1 over x squared when x is not 0, and then when x is 0, it's negative 1/2, because if this worked for 0, then you'd plug in 0 here and be undefined, right? Okay, so we have the function f defined above has derivatives of all orders. What does that mean? That means that the first derivative exists, the second derivative exists, the third derivative exists, all n derivatives exist, no matter how high you go. That's important for Taylor series, right? So then they say g is this function divided by 1 plus the integral from 0 to x of f of t dt. That'll probably come into play later. So the first thing they want is the first three non-zero terms, the general term for the Taylor series for cosine x about x equals 0. This is one you should have memorized, right? It's one of the big three that you have to know. So cosine x, remember that's the evens. Cosine x is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. They want the first three non-zero terms, so that's enough. So I'm going to do minus dot dot dot. And then the general term, sometimes they'll just do like, they'll add it right there, but I'm just going to do it as a sigma. So it's sigma from n equals 0 to infinity, because hopefully you know this. It's negative 1 to the n, x to the 2n over 2n quantity factorial. So you could just put that after the dot dot dot, but I like to put it in terms of sigma. So they want us to use that to write the first three non-zero terms and the general term for the Taylor series for f. So what we're going to do, so their hint here is that you can use the cosine one to be able to figure out f, because if you start taking derivatives here and center it at x equals 0, you're going to end up with non-defined terms, right? This x squared is going to be 0 all the time, and it's not going to work out. But if you use this cosine, and you just plug it in where that cosine is right there, then it's going to work. So let's do that. So let's just put it where that cosine is. So f of x, if I put the cosine in, so it's going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus blah, blah, blah. I'm actually going to put one more term in there. So we'll have an x to the sixth over 6 factorial. Doesn't really matter. You don't have to have that, but I like to go just a couple more so you can really get a good idea of the pattern. So then we have minus 1, and that's all over x squared. Okay, so all I just did was wrote this using that first term. Now you might be saying, well, what about that x equals 0? Don't worry about that for now. We'll see if it works out when we get to the end. If it doesn't, we might have to change a constant or something. We'll just see what happens. So now what's going to happen here? Well, I have a 1 and a negative 1, so those just cancel out. And the rest of them looks like my first term is negative x squared over 2 factorial, then x to the fourth over 4 factorial, and I'm dividing everything by x squared. So you could think about pulling a 1 over x squared out of this. We've been struggling with that this year, being able to pull fractions out to the front. So I'm just going to write it like that. So 1 over x squared times negative x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus blah, blah, blah. So you should be able to see just from this, though, up here, that you're just going to be reducing all the powers by 2, right? So these 1s are gone. So you're going to divide everything by x squared, so x squared over x squared is just 1. So this is going to be negative 1 over 2 factorial. And then it's going to be plus x squared over 4 factorial instead of x to the fourth, and then minus x to the fourth over 6 factorial, etc., etc. So there's our first three non-zero terms. We got them right there. They also want the general term. So let's see if we can figure that out. So that's going to be sum. Let's start at 0 again to infinity. This is a little bit tricky because basically on the top we just have x to the 2n, right? We have a negative 1. This time I have to do the n. I'm going to do plus 1 because I need to start at a negative number, right? If you just do n, that's going to start at a positive number. So I'm going to have x to the 2n on the top, right? Because we start at no x at all, then 2, 4, 6, 8. So kind of just like cosine. But then on the bottom, this is where it kind of becomes tricky. I have to start at 2 factorial. So I can't just do 2n factorial. Right? If I do 2n factorial, think about what that generates. That generates 0, and then 2, and then 4, and then 6, and then 8. So I kind of want that, right? But I don't want to have the 0 at the front. So what I want to do is I want to start 1 later. So to do that, I just add 1 to the n. So I have 2 times n plus 1 factorial. There are other ways to do that too. Sometimes people do 2n plus 2 because you're just adding 2 to all the ones that you want, right? You don't want 0, you want to start with 2. Then you don't want 2, you want 4. Then you don't want 4, you want 6. But if you distribute the 2, it's the same thing. So you can do 2n plus 2 factorial on the bottom there too. Okay. Alright, so there we go. We have our general Taylor for f. Let's see what happens when we plug in 0. If you plug 0 into this, everything cancels out except for the negative 1/2, which is exactly what they tell me f of 0 is. Thank goodness. So that works out. Alright, let's see what else they want us to do. So now they want us to use the Taylor series for f to determine whether f has a relative maximum, minimum, or neither at x equals 0. So this is digging back a little bit, but this is what they do. They mix all of the parts of calculus together in one problem. So let's just go back to what happened. So let's draw what a max would look like, draw what a minimum would look like. Well, a maximum would be where we have a derivative of 0, right, because we have a horizontal slope. Minimum, same thing. So first thing we should check is to see if the first derivative is 0. So I'm trying to remember, I think the first few terms, we had negative 1 over 2 factorial, we had plus x squared over 4 factorial, then minus x to the 4th over 6 factorial, x to the 6th over 8 factorial, right, this pattern keeps going. So we take the derivative, so this is f of x. Take the derivative, f prime of x. F prime of x, the constant would go away. I would have 2x over 4 factorial. There's another question I've been getting a lot is, why don't you have to derive the 4 factorial? What is 4 factorial? It's a constant, right? Don't forget your fundamentals with derivatives. The derivative of like x squared over 10. Some people are using quotient rule on this. Don't do that, right? This is 1/10 times x squared, right? Fractions. This is like back to middle school math. So the derivative of this would just be 1/10 times 2x. Or you could have just left it on the top and moved the 2 to the front, 2x over 10. It's important that you have these fundamentals down. Okay, so let's forget about that. My rant is over. And come back to here. So 2x over 4 factorial will be minus 4x cubed over 6 factorial, then plus 6x to the 5th over 8 factorial. And we evaluate that at x equals 0. So they're asking what's going on at 0, right? So we want to plug in 0 and see what happens. Well, that means the derivative is 0, because there's an x in every single term. So this is so far so good. We have a horizontal tangent. Now, for the next part, what a lot of you remember is you remember the number line thing where we did like changes. A maximum would change derivative from positive to negative. A minimum would change from negative to positive. The problem is with series, because it's alternating the whole time, it's tough to plug in something just to the left and just to the right, because I don't know where all the other zeros are. It'd be really hard to do because you have an infinite degree polynomial. I don't know how many zeros this has. So it's tough to pick something close enough, right? Because even like 0.0001, it's possible there's a 0 between these two, right? So I can't really do that. So what I have to go to is, you might remember, what's the difference between these in a different way? Well, this guy is concave down, like a frown. This guy is concave up like a cup. So if I do the second derivative, and I find out if it's negative, that means it'll be a maximum, and if it's positive, that means it'll be a minimum. So let's do the second derivative. So the second derivative of x is going to be 2 over 4 factorial. Minus 12x squared over 6 factorial, plus 6x to the 4th, 30x to the 4th over 8 factorial, etc., etc. If we plug in 0, we get 2 over 4 factorial. Now what's the important thing there? Some of you will be like, well, that's 1/12, right? Okay. The important thing is it's greater than 0. That means that at this moment, at 0, this function is concave up. So always draw a picture. Concave up. Derivative is 0. This is a minimum. That is the second derivative test we just used there. Okay, a little bit of review from back in chapter 3. Okay, so this is a minimum. And you could write, because f prime of x is 0, and f double prime of x is greater than 0. Okay, so concave up means we must have a minimum. Okay. All right, what else? Okay. Now they want us to do with g. So at the 5th degree Taylor polynomial for g about x equals 0. So some of you might be tempted to start doing g of 0, g prime of 0, g double prime of 0. This will work, but they hardly ever ask you to do a 5th degree with something like this because it's just too much work. And also you can start running into problems with doing derivatives of this guy because you never had to take any derivatives of this guy. You have to do quotient rule and it's just a big pain. The first derivative isn't too bad, right? You just dump in the x. The second derivative is the derivative. But there's an easier way to do it. We have a series for f of x, right? This is kind of like what we had for the geometric series. We have a series for f. So g of x, let's just rewrite this. 1 plus the integral from 0 to x. We know the series for f, right? It's negative 1 over 2 factorial plus x squared over 4 factorial minus x to the 4th over 6 factorial, x to the 8th over, 6th over 8 factorial, blah, 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 dx. Okay, now let's just antiderive this. So this is 1 plus negative x over 2 factorial plus x cubed over 3 times 4 factorial minus x to the 5th over 5 times 6 factorial. How many terms do they want? Well, let's go to the number that we have here. Plus x to the 7th over 7 times 8 factorial. Blah, blah, blah. Okay, and they want the 5th degree, so I can stop at the 5 there. Okay, and this is going to be from 0 to x. I guess these should be t's, that's my fault. All of these should be t's. Can't have x's in both places, Fransky. There's a t, there's a t. I think in my solutions online I also did that by accident the first time. So these are also all t's. Antiderivative there. T here, t here, t here. Now I'm going to plug in x and I'm going to plug in 0. Well, plugging in 0 is pretty much uneventful, right? Because everything's going to go away. So this becomes 1 minus x over 2 factorial. X is correct next, I'm plugging it in. Plus x cubed over 3 times 4 factorial. Minus x to the 5th over 5 times 6 factorial. And they only ask for a 5th degree, so that is where I'm going to stop. All right. So a term-by-term anti-differentiation there, right? All right, so now they say the Taylor series of g about x equals 0 and x equals 1 is an alternating series with individual terms. This is something you can't do until you've done 9.5. It's an alternating series. So the alternating series, basically they're listing all the criteria for the alternating series test. They all have to be positive terms that decrease to 0 in absolute value, and then we use the 3rd degree polynomial about x equals 0 to estimate the value of g of 1. So g of x, g3 I guess we could call it because we're doing the 3rd degree, 1 minus, was it x over 2 factorial? And then it was plus x cubed over 3 times 4 factorial. And then minus x to the 5th over 5 times 6 factorial, right? And we want to use the 3rd degree to be able to do this. So alternating series, what it says is that the error is bounded by the next term. It's so easy. Okay? And if you haven't done 9.5 yet, you'll learn that soon. Excuse me. So the next term is x to the 5 over 5 times 6 factorial. Okay, so that is x to the 5 over 5 times 6 factorial. And they want us to estimate the value of g of 1. I didn't do that. So we're going to, so g3 of 1 is going to be 1 minus 1/2, because 1 over 2 factorial is just 1/2, plus 1 over 3 times 4 factorial. 4 factorial, 4 times 3 is 12, times 2 is 24, times 3 is 72. I'd probably stop right there, right? You could find a common denominator. This is 72 minus 36 plus 1, so it'll be 37 over 72. Double check my math on that. That was a little quick. But that the error is going to differ by most of the next term. We're going to evaluate that at the value that we used, x equals 1. So that is 1 over 5 times 6 factorial. And they want us to show that it's less than 1 over 6 factorial. Well, yeah, absolutely, because this is 1 over 5 times 6 factorial. It's going to be a smaller number. So that is for sure true. Okay, so the error is bounded by even a smaller number, so it must be bounded by 1 over 6 factorial. All right, that's problem 1. Numero dos. Yeah, so a function of f has all derivatives of all orders. Pnx is the nth degree Taylor polynomial about x equals 0. So it's the Maclaurin series, right? So Pnx, I'm just going to write it out. I think this is always smart. You can never write this enough times. It's really good practice. F of 0 plus f prime of 0x plus f double prime of 0x squared over 2 factorial plus f triple prime of 0x cubed over 3 factorial. And they say it's going to stop at n. So I'm going to stop it at the nth derivative of 0x to the n over n factorial. No dot dot dots at the end because it's stopping. It's the nth degree Taylor polynomial. So now they tell us that f of 0 is negative 4. Sounds like I can put that right here. And the first order Taylor polynomial of 1/2 is negative 3. So notice they put a 1 here. Okay, so first let's figure out what would p1 of x be. Okay, keeping in mind what pn of x is. So you stop on the nth power of x. So that's just going to stop at x. So that's f of 0 plus f prime of 0 times x. That's it for p1 of x. Now I'm just going to put in what they tell me. They tell me p1 of 1/2. So I'm replacing the x with 1/2. I get nervous sometimes. Some people are having trouble plugging x values into functions. Okay, so I'm just plugging 1 in here for where the x is. And then they tell me f of 0 is negative 4. So it's negative 4. F prime of 0 is what I don't know, and I'm trying to prove, times 1/2. And they tell me that it's equal to negative 3. So we solve. Add negative 4 to both sides. Excuse me. So we have f prime of 0 times 1/2 equal to 1 multiply both sides by 2, f prime of 0 is 2. So it's kind of like f prime of 0 is a variable you're trying to solve for. This comes up a lot in these problems. Sometimes I ask for like the 7th derivative of 0, and you just have to look at the polynomial and say, well, it's whatever's sitting in front of x to the 7th divided by 7 factorial, right? So now they tell us f double prime and f triple prime. Notice to find p3. So p3 of x, not bad to practice this, right? F of 0 plus f prime of 0x plus f double prime of 0x squared over 2 factorial. And then f triple prime of x cubed over 3 factorial. So let's plug in what we know. We know f of 0 is negative 4. Right? They told us that in the last problem. We now know that f prime of 0 is 2. Now they tell us the second derivative is negative 2/3 times x squared over 2 factorial. They tell us the third derivative is a positive 1/3 times x cubed over 3 factorial. Now I'm going to clean that up a little bit because I think it's going to be useful for the next problem. So that is negative 4 plus 2x. To negative 2/3, the 2's cancel, right? Because 2 factorial is just 2. So this is minus x cubed over 3. X squared over 3, excuse me. And then we're going to have plus, let's see, 3 times 3 is 6 times 3 is 18. So it'll be x cubed over 18. So that's kind of the prettiest way we can write that third degree Taylor polynomial with that 18 crossed off there. Sorry about that. All right, so let's see what they want next. The function h has first derivative given by h prime of x equals f of 2x. It is known that h of 0 is 7. Find the third degree Taylor polynomial for h at x equals 0. All right, so h prime of x is f of 2x. So here's what I'm going to write. F of x is, we know from the last problem, negative 4. Let's see if I can remember it. Plus 2x. Then it was minus, I think it was x cubed over 3, was it? X squared over 3. Let me double check that. I don't trust myself. X squared over 3, and then plus x cubed over 18. So we have plus x cubed over 18. They only want the third degree, so I think this is going to be enough terms to be able to use for h. So that means that f of 2x, right? We're just plugging it in. This is kind of like a building block thing. So I'm going to replace, if f of x is negative 4 plus 2x minus x squared over 3, I'm going to replace all the x's with 2x. So that's going to be negative 4 plus 2 times 2x minus, not plus, 2x quantity squared over 3, and then plus 2x quantity cubed over 18. Let's clean that up a little bit. So this is equal to h prime, right? Because they tell us h prime is f of 2x. So I'm going to write h prime of x is equal to, let's clean this up. So you have negative 4 plus 4x, and then minus, this would be 4x squared over 3. Let's see if we can do this math in our head. 2 cubed is 8. Out of 18 is 4/9. So it's going to be plus 4x cubed over 9. So this is h prime. If this is the derivative, they want me to find it for h. So I need to find h, I need to anti-derive, right? So I'm going to anti-derive both sides. So we have h of x. It's going to be equal to negative 4x plus 4x squared over 2, right? We're just anti-deriving. Minus, let's see, it'd be 4x cubed over 9 now. And then plus, let's see, this would be 4x to the 4th over 36. But they only want third degree, so I don't care about that one, right? And then now this is where it gets a little bit sneaky. We have plus c. Because it's not a definite integral. It's an indefinite integral, so we have to have a plus c. Now what do they tell us? They tell us that h of 0, which, let's see, everything goes away here, so it's just c, is 7. So c is 7. So h of x, h3, I guess you could write of x because it's the third degree polynomial, is going to be equal to, so c is 7, so I'll start with that. So 7 minus 4x plus 4x squared over 2 is 2x squared, minus 4x cubed over 9. And there you go. A little bit tricky. Not impossible, right? It's a puzzle. I love these problems. I give you just enough information to do these. All right. 2x over 1 plus x squared. Your spidey sense for a geometric series should be buzzing, right? This is a over 1 minus r. If you did this problem already and you did it with a bunch of derivatives, you did way more work than you had to do, right? So they want the first 4 non-zero terms and general term for the Taylor series for f about x equals 0. You could start doing derivatives, but you're going to be in quotient rule for a long time. Don't want to do that, right? A is 2x. R is negative x squared. So what do we got? We got 2x minus 2x cubed plus 2x to the 5th minus 2x to the 7th. They just want 4. Yep. Okay. And the sigma, so I'm going to start at 0. You could start at 1, either way. So 0 to infinity, it's going to be 2x times negative x squared to the n. You can also do it with a negative 1 up front, so n equals 0 to infinity negative 1 to the n, because the first term is positive, that's just fine. And then it'd be 2x times x squared to the n. Either way, right? All those are good. So next they ask, does a series found in part A when evaluated at x equals 1 converge to f of 1? So f of 1 we could find, right? It'd be 2 over 2, so it'd be 1. So f of 1 we know is 1. So the question is now, if we plug 1 in here, and here, and here, and here, and here, and here, is it going to converge to the same thing? Well, if you actually start plugging it in, let's see what happens. First term is 2, then minus 2, then plus 2, then minus 2, then plus 2. What is this doing? It's oscillating, right? 2, 0, 2, 0, 2, 0. So we know the answer is no. We should probably have a better answer, right? So right there you could say it oscillates. But we could do this mathematically. So we know that geometric series converge only when converge. That's close. There we go. When absolute value of r is less than 1. In this case, that means absolute value of negative x squared has to be less than 1, which means negative 1 less than negative x squared less than 1. So if we multiply everything by negative 1 and flip the signs, so 1 greater than x squared greater than negative 1, and then we take the square root, that means that x still has to be between negative 1 and 1. Okay? Notice it's not less than or equal to. So no. Because the geometric only converges when it's less than 1, so between negative 1 and 1, but not included. So not included in the interval is what I would say. Cool. All right, let's see what's next. So now they tell us that the derivative of natural log 1 plus x squared is this guy, right? Chain rule, okay? So that would come up to the top. They want the first 4 non-zero terms of the Taylor series for ln of 1 plus x squared about x equals 0. So I'm going to rewrite this out. It was 2x minus 2x cubed plus 2x to the 5th minus 2x to the 7th, etc., etc. So they have the first 4 non-zero terms. We got 1, 2, 3, 4 here, so it should work. So if the derivative of natural log is this, to get from here to here, I would have to integrate, right? So natural log of 1 plus x squared will be equal to the antiderivative of 2x minus 2x cubed plus 2x to the 5th minus 2x to the 7th, blah, blah, blah. Okay, that is, let's see, just x squared minus 2x to the 4th over 4 plus 2x to the 6th over 6 minus 2x to the 8th over 8, etc., etc. They want 4, 1, 2, 3, 4. That'll do it. So we could simplify here. X squared minus x to the 4th over 2, and then plus x to the 6th over 3 minus x to the 8th over 4, etc., etc. There it is. Cool. You also might notice this is just we did one of our kind of ones that we had as a building block was ln 1 plus x. That was x minus x squared over 2 plus x to the 3rd over 3, blah, blah, blah. If you just replace all the x's with x squareds, because you replace the x with x squared here, you end up with this series. Nice. So now they want us to use that series. This is a 9.5 problem again, I think. To find a rational number a such that a minus ln of 5/4 is less than 1 over 500. So what they want us to do here, so they're asking us to find the error. Right, so the rational number, so this is going to be the approximation. This is the exact. Okay, so ln of 5/4, that's ln of 1 plus 1/4. Okay, and this was a series for ln of 1 plus x squared. So it looks like this is evaluating when x is 1/2, right, because that's ln of 1 plus 1/2 squared. Okay, so what they really want us to do here is to use the series. Okay, so they want us to see how many terms we have to use in order to make sure that the error is less than 1 over 100. So we can just start guessing number of terms. It's an alternating series. Okay, they often do this with alternating series because it's easy. That means the error is bounded by the next term. So if we only use x squared, so using, let's say, approximately, that'd be 1/2 squared. So that we're saying, is that close enough to natural log of 5/4? I don't have a calculator, so I can't check it. But what I can do is say, well, I know that in that case, the error would be bounded by the next term, which is x to the 4th over 2. Okay, so x to the 4th over 2, evaluated at x equals 1/2, would be 1/2 to the 4th is 1/16 over 2. That's 1 over 32. So the error would be bounded by 1 over 32. We need to be smaller than 1 over 100, so that's not going to work. So let's try using two terms. 1/2 squared minus 1/2 to the 4th over, what was it, 2? Because I had it right here. So then the error would be bounded by the next term, which would be x to the 6th over 3. So it would be x to the 6th over 3. Evaluate that at x equals 1/2. That would be 1/2 to the 6th. Let's see, 2 to the 6th is 64. So that's 1/64 over 3, which is 1 over 3 times 64. 3 times 64, let's see, 180, and 12, it's 192. Hey, that's less than 1 over 100 for sure. Okay, so two terms are going to be enough because the third term bounding it's going to be good enough. So if two terms work, now we have to actually find the rational number. Now, because they say rational number, I think we have to calculate it out. Because writing it like this, it's easy, but it's messy, right? So this would be 1/4 minus, we already did this, 1/32. Right, we found that up here. Okay, so this is, if we multiply by 8 on the top and bottom, 7 over 32. So 7 over 32 is within 1/100th of the actual value of natural log 5/4. Could check that on a calculator. That could be kind of fun. But right now we're going to move on. All right, so now, I think this is the last one on the page. Pardon me while I'm dying over here. So we have the function given by 6e to the negative x over 3 for all x. So now the first four non-zero terms, the general term for the Taylor series for f about x equals 0. So, few ways to do this. I'm trying to remember how I did it on the solutions. I don't know. I'm going to decide as I go here. But, so remember the Taylor series. Taylor series is, I'm trying to think of how I want to do this. I'll do it both ways. Why not? So Taylor series, f of 0, you can decide which one's easier. Plus, because we're setting it at 0, so plus f prime of 0 x plus f double prime of 0 x squared over 2 factorial. Plus f triple prime of 0 x to the third over 3 factorial. They want four non-zero terms. I think that's going to do it. So f of x is 6e to the negative x over 3. So that means f prime of x is going to be, let's see, negative 1/3 times 6e to the negative x over 3 because of chain rule, right? You leave the e to the x alone, multiply by the derivative of the exponent. And then that means f double prime of x is going to be negative 1/3 times negative 1/3 again times 6 e to the negative x over 3. We need one more. So f triple prime. Looks like these keep stacking up, right? So we're going to have negative 1/3 times negative 1/3 times negative 1/3 times 6e to the negative x over 3. Let's see if it's going to fit there. There we go. Okay, that's a 6 there. So let's start evaluating these at 0. So f of 0 is just going to be 6, right? Because 6 times 1. F prime of 0 is going to be negative 1/3 times 6, because e to the 0 is still 1. So that's going to be negative 2. F double prime of 0 then is going to be, let's see, so this is still 1. So we have 6, it's going to be a positive 2/3, right? Because 6 divided by 3 is 2, divided by 3 again, 2/3. Then f triple prime of 0 with a little bit more room this time. Looks like we're going to have negative 6 over 27, right? Because we have 27 on the bottom. All right, so then the first four terms are going to be 6. And then it'll be, so f prime of 0 times x, so minus 2x. And then it'll be plus 2/3 x squared over 2 factorial. Right, just putting them where they belong. And then minus 6/27 x to the third over 3 factorial. And I'd probably just leave it like that. Okay, you could do some combining, right? This 3 over 2 would be 6. So this would turn into 1/3. For 6/27, so 3 factorial. The 6's would cancel. Actually, this isn't too bad. Let's just simplify it. 6 minus 2x plus x squared over 3. The 6's would cancel here. So then it would be minus x cubed over 27. That might be easier to deal with. Okay. Now, I said there are two ways to do it. The other way you can do it is using building blocks, right? We know e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. How many do I need? I think that's it. So then if I multiply the entire thing, or if I change all the x's to negative x over 3, so I have 1 plus negative x over 3, and then plus negative x over 3 squared over 2 factorial, and then plus negative x over 3 cubed over 3 factorial, and multiply the entire thing by 6. If you do the work, you're going to end up with the same thing, right? You can see the first two terms work out, right? 6 and then minus 2x. The next one you'd have to do a little bit more legwork. I'm not going to do that right now, but you end up with the same thing. I don't know which one's easier. Up to you. All right, so now they tell us g is the function given by integrating from 0 to x f of t dt. So they want us to find the first four non-zero terms and the general term. So we're going to integrate 0 to x of the series. So we have 6 minus, let's do this one, 2x plus x squared over trace minus x cubed over 27 dx. Okay, so antiderivative, 6x minus just x squared plus x cubed. This is pretty handy. And then this would be minus x to the fourth over 4 times 27. Oh, I did something wrong. This should be x cubed over 9, right? Mr. Fransky, 3 was not in front, it was down below. Okay, and that's from 0 to x. When we plug in 0, everything disappears. So we only have to worry about the x. I guess I should have put a t in there. I'm not going to change it back now. So this is indeed just 6x minus x squared plus x cubed over 9 minus x to the fourth over math in my head, 80 and 28, 108. There we go. Okay, just by integrating, right? It has nothing to do with integrating this function at all, right? Integrate the series term by term. Way, way easier, right? All right. So let's see now. This is a completely different problem, right? This is another example where they kind of reset it after you've done a few other problems. So function h satisfies h of x is equal to k f prime of ax. Ooh, two constants. How fun. For all x where a and k are constants. The Taylor series for h about x equals 0 is this guy. Hopefully when you look at this, it jumps out to you right away. What is that series? That's e to the x. So h of x is just e to the x. So they're telling us is that e to the x is equal to k f prime of ax. Okay? So what I'm going to do now is just start doing work on this function right here. So they tell me e to the x is equal to k times, let's figure out what f prime of x is. So f prime of x, we did it on the last slide, it would be just negative 1/3 times 6e to the negative x over 3, which is negative 2e to the negative x over 3. So that means that f prime of ax, if I just replace the x with an ax, so I have negative 2e to the power negative ax over 3. Okay, so k times negative 2 times e to the negative ax over 3. All right. So let's see what's going on here. So we have e to the x is equal to negative 2k e to the negative ax over 3. So these have to be equal. That means that the exponents have to be the same and the constant in the front has to be the same. Well, notice that the constant in the front here is technically 1, right? So negative 2k has got to be 1. So what's k? You could make an equation, right? Negative 2k equals 1. All right, or you could just look at it and say, well, k is negative 1/2. There we go. Okay, so k is negative 1/2 because it has to cancel out the negative 2 to make the 1 in the front there. Now the exponent here, notice here we just have x. Over here we have negative ax over 3. I need the negative and the 3 on the bottom to go away. So it looks like a is what? Again, you could probably figure it out, but negative a over 3 has got to be equal to 1. So that means that a is negative 3. There we have our two constants that make this work out. Okay. All right, I think that is it for the blue sheet. Yay! Excellent. Love you guys. That's why I'm here. Have an excellent day.